Hello and welcome to my talk. I'm Giulio Lovisotto, and this is the presentation for our paper where we improve physical adversarial examples with short-lived adversarial perturbations, which we shorten with SLAP. This is a collaboration between the University of Oxford and armasuisse. Let me begin with the context and the motivation behind this work. I've reported this clip from the Tesla autopilot. I'd like you to notice how many things are happening simultaneously. There are multiple deep neural networks that perform a set of various tasks, such as detecting objects in the frames or detecting lanes. And all of these predictions are eventually combined to decide where to drive the car. In this scenario, but really in any scenario where a system acts based on neural networks that use camera inputs, we need to ask ourselves about the security of the system. In particular, is there any way that an adversary can alter a scene as it is perceived by a camera so that the altered scene deceives the neural network into making wrong predictions? If you are familiar with this field, you might know that previous work found that you can create adversarial examples, inputs that fool a network, in the real world by applying specifically crafted patches onto objects, such as stop signs. However, we know that patches have some limitations. We know that they introduce detectable behavior because the patch introduces a small area of high saliency for the network. So things such as Sentinel might be able to detect it. And that the modification they can cause is static, so it might be conspicuous to an observer. We wonder if there was any other attack vector to realize these scene alterations. In particular, what if we use an RGB projector to shine a specifically crafted perturbation onto some object? Using this attack vector, we overcome the two limitations of adversarial patches, because now we can turn easily the projection on and off, and we also don't introduce those small areas of high saliency that make the patch behavior detectable. The first challenge to finding the perturbation to project is to address the realizability of colors. And we found that the best way to do this is to approximate the color space using a neural network, because this overcomes the limit of non-printability score, which has been used previously to solve a similar problem with patches. To fit such a network, we designed a procedure where we picked a certain target object, for example, a stop sign. Then we projected a quantized subset of all the projectable colors one at a time. And doing so, we could collect three different values: the original surface color that we are projecting on, the projected color, and the resulting surface color. We use these triples to fit our network, which we call the projection model, or P in this formula. We did this by minimizing the sum of absolute errors between the network prediction and the ground truth resulting color. And this is what it looked like in practice. This 3D plot shows an example of the resulting color space. For this, I have fixed the surface color to be either the red or the white pixels that you find on a stop sign, and I'm projecting a set of random colors. The plot shows that the model has learned that the two clusters of red and white remain separated. The red pixels will generate various shades of red, while the white pixels will generate shades tending towards cyan or blue. The second challenge that we addressed is to improve the robustness of the adversarial example to environmental changes, things such as looking at the object from different distances and viewing angles. Here we can use the expectation over transformation method, where we minimize the loss across a variety of generated inputs. Here we have a certain randomness component that will select a random image background and place the target object onto the background after applying a set of affine transformations. Then the generated image will be used in our iterative optimization. Here we feed the image together with the projected image into the projection model, which will tell us what's the effect of projecting this image onto that object. Then we feed the result to the target network, that is the network in charge of detecting stop signs, for example. Because we made sure that the projection model was differentiable, we can now use gradient descent to backpropagate the whole way from the output of the network into the projected image, which is the variable that we optimize. We designed a real-world valuation where we investigated various target networks across a variety of lighting conditions. In fact, if you ever try to use a projector outside, you will know that in brighter ambient light, the projector-induced changes will degrade quite quickly. In each experiment, we first took a baseline performance measurements where we measured the detection of the target object in normal non-adversarial conditions. This is what it looks like for the YOLO V3 network. You can see that the detection works flawlessly in this script as the network is detecting a stop sign and drawing a red box around it. Then we project our perturbation computed with SLAP and take the same set of videos. You can see here that the sign is not detected any longer, and this is the same model. We also did the same experiment outdoors in moving vehicle settings, such as in this clip, which was taken before sunset roughly at 200 lux of ambient light. We measured the misdetection rate, that is the number of times a stop sign is not detected. We use all of the videos that we collected across various distances, various angles, and ambient light conditions. And to give you an idea, to make one of these cones showing the misdetection rate, we use thousands of frames. Each frame has been forward passed onto the network. This is what the attack success looks like for YOLO V3. You can see that in a baseline scenario with no attacker present, we have very low misdetections. So the stop sign is reliably identified. However, as soon as we turn on our projector, we can get to very high misdetection rate, often over 95% across most of the cone, showing that SLAP deceives the network consistently. Here are some of the results under varying light conditions. You can just focus on the shades here, where a darker blue means that the attack is more successful. If we start at the bottom with relatively low light, roughly what you would find indoor and 120 lux, we can see that generally we have high success rate. These cones for each model have quite dark shades. However, if we increase the ambient light, and we did so in our experiments with the help of additional artificial lights that we aim at the stop sign, the attack slowly degrades at 300 lux and even more when we reach 600 lux of light, to be almost ineffective for most networks at this ambient light level. We looked at 3 different adversarial example defenses to see whether SLAP might be detected. The first one is adversarial learning, where we retrain the network with an adversarial loss. In other words, we force the network to classify correctly even hard to classify examples. Then we consider input randomization, which uses simple transformations such as resizing and padding to make sure that a certain adversarial example loses its adversarial properties and is therefore classified correctly. Then we also consider Sentinel, which is specifically designed to detect physical adversarial examples. What Sentinel does in brief is it will look at the input, it will find input areas that affect the network decision the most, and then it will compare the behavior of samples where we overlay these salient areas. If a sample is adversarial to begin with, then the overlaying will generate a detectable behavior. Here is again the success rate when we apply these defenses. We can see that Sentinel doesn't detect the attack. The success rate remains above 90%. And this is because the salient areas that we are introducing with the projection now cover the entire object. Similarly, input randomization is countered by the fact that we are using expectation over transformation. And finally, we can see that adversarial learning can stop the attack. However, it remains to be seen whether this holds against adaptive attackers. If you followed the talk so far, you might have noticed that I've mentioned target objects a lot, but I've only really shown you results with stop signs. Well, our goal was to introduce a general capability of altering scenes, so we tested different objects as well. Here we've chosen a bottle, and we applied the same pipeline to craft the projected image. And this is how it works in practice. These 2 models can easily detect a bottle in a baseline scenario with no attacker. However, when we shine the specifically crafted perturbation, we find that the first network now has some confidence that this is instead a toothbrush, and in the second case, the bottle is not detected at all. We repeated the same for the giveaway sign, and we got similar success. In a baseline scenario, we have high confidence of this image being a giveaway sign. However, when we shine the adversarial projection, this becomes a work in progress sign in the case of GTSRB CNN, and actually a speed limit to 45 miles per hour in the case of LISA CNN. In conclusion, we demonstrated that SLAP works robustly in the real world for both image classification and object detection, depending on the ambient light conditions. We didn't find any straightforward defense that could detect SLAP, and considering adversarial learning with adaptive attackers and defenders might end up in an arms race. I would also like to highlight how SLAP introduces new capabilities for adversarial example-based attackers, the ability to alter the scene content dynamically, in particular for tasks that make use of overtime information, such as video frames, when the model has memory, whether this is a recurrent model or implements memory with attention layers. We now have the capability for new attacks that were not possible when using adversarial patches. This highlights the practical need of a new type of adversarial robustness for sequential data. That's the end of the talk. Thanks very much for your attention. Let me say that we happily went through the artifacts evaluation for this project, and we would like to thank the reviewers for the useful feedback. As a result, we also published a set of functionalities that we use in this project in our GitHub repository, which is available at this link. Thanks very much.